Okay, shall we, so we have until 10, the first.
I don't have the schedule memorized at the moment.
Okay.
But I can double check.
Yeah, I can go until 10. Yeah.
Okay.
That should be good.
Sounds
yeah.
good.
Okay. All right. Good morning, everybody. Okay. I'll introduce myself a little bit. My name is Yiluan. I'm currently a postdoc in MIDAS. I'm working with the Schmidt and Science Postdoc Fellowship. And then my background is actually in environmental data science and global change biology. I work a lot with SEAS, which is the School of Environment and Sustainability here. I also work closely with the Department of Statistics here. And most of my research are actually on the seasonality of the biological systems. For example, when trees have their flowers, so on and so forth. And in recent years, I've really been interested in integrating machine learning with our domain knowledge. And that's why I'm here to introduce to you physics-informed neural networks. So I'll be clear that I'm a recent learner of this method. So hopefully my experience sharing this with you will make it accessible to us, especially to those like me who don't exactly work in physics. Okay, can you all hear me well? All right, let's dig in. Okay, first, let's try to define pins and see what they are. So this is still a type of deep neural network, but the special thing is that it incorporates physical laws, and these physical laws are expressed as partial differential equations. And later we're going to talk more about what these partial differential equations look like. So when we talk about PDE, you can think of it as, at least in this context, is the way that we embed physical laws into neural network. And this method embeds the physical laws directly into the model training process. The expected result of this model is that we want a perfectly trained neural network that does two things. One, it fits the data. At the same time, second, it respects the physical laws. So how does this look like in the architecture? So we will have our input. In our usual neural network, you probably see a set of predictors as input. For example, you want to use time, and you want to use the environmental variables like temperature as your input. For pin, we typically have the input coordinates in space, and we can also have the coordinates in time. So these space and time coordinates are the input of this neural network. It will pass through a very typical neural network structure, and it will give us the output, which are physical quantities. And these physical quantities might be things like velocity, might be pressure, or might be temperature, something like this. And these physical quantities, they can do two things from here. One is that you can directly compare it to your training data. For example, if you have predicted with this neural network velocity in a field, and you have observations at points in this field about what the velocity really should be, you can compare them at this point. So far, up to here, this is not very different from a typical neural network. It's just that for input and output, we are quite specific about what they are. But the second thing we can do with the output is that we can compute the derivatives based on these physical quantities over our input. So for example, our physical quantity output is u, and our input coordinate is x. We can calculate du over dx, or the second order derivative, or even higher. So these derivatives are later, we evaluate them to see how well they fit the PDE that we have in mind. And we try to minimize the difference between the derivatives that we calculate after equation. We try to minimize the equation residual. And later, we're going to talk more about how to calculate this residual. But mainly, it means that once we have a PDE and we plug in all the derivatives that we calculated from the model output, how different it is from our expectation. If it's very different, we penalize the model. And I want to give a brief justification of why we need to use pin. And I specifically bring a real-life example. If you play games, you probably have noticed that it's so hard to simulate water dynamics. And these are some of the top games that simulate water dynamics really immersively. But you also notice that in these games, this kind of simulation takes a lot of compute because sometimes you realize your laptop is heating up or is lagging. So these are signs that this is a very expensive calculation to do. Why is it so expensive? Because usually we use numerical method to simulate this kind of water dynamics. And what are the numerical methods based off? So they're essentially based off PDE like this. In the context of fluid dynamics, this is a very popular, commonly used equation called Navier-Stokes equation. This has the general form that it has velocity and pressure gradient as the output, and it has external force as the input. It's also determined by parameters like density and viscosity. So you can imagine that at any given point, your velocity might be affected by so many things. For example, the external force, whether this water is coming somewhere with a force, whether you're throwing a ball of water out, is determined by the previous velocity, or the neighbor water particle's velocity. It's also determined by these parameters, like whether this is water or mercury, or whether this is water or honey that has different viscosity. So this is what this equation is trying to describe. And often in the simulation, we use variations of this. But my point is that when water flows in a game, it often follows this PDE. And they are very complex to solve analytically, and often does not have a great exact solution. So what we have to do is that we simulate from one time point to the next, and in the game engine, we will simulate from one frame to the next to see how this water will change frame by frame. And this kind of simulation is called the numerical method. And this is why this is such an expensive computation. So now we talked a little bit about numerical method. What will be the alternative of numerical method? So we mentioned that numerical method, if it's on one dimension, if you only have time, you predict from one time point to the next, it's probably still okay. But if you're facing a very high dimensional problem, like the ones we mentioned in the game, we need to simulate water over 3D. In that case, it's very hard and often impractical. So we can use pin as an alternative to this numerical method. Especially for these high-dimensional PDE, pins are often very efficient. Another challenge for the numerical method is that they often require mesh or grid. In other words, we need to know where we want to predict at. For example, in a game, we know that we have these many pixels on the screen. I want to simulate at every pixel. That's fine. In a more realistic hydrological simulation scenario, we have this very complicated coastline. And then we have to think about where do we want to make prediction at if we want to predict how this river is going to flood. Then we might have to generate this mesh in gray color in the background. So in relatively simple terrain, like very far away from the river, we probably don't need high resolution prediction. We can have this sparse mesh. But when we get close to the edge, to the riverbank, we need really fine mesh, really complicated mesh. So this mesh generation for numerical methods is still complex. It is still a challenge. And also, if our point of interest falls off this grid, we don't have a prediction, essentially. And we have to interpolate them, which is still very inaccurate. So here, if we use the alternative of pin, the advantage is that it is mesh-free. It means that, okay, forget about the mesh. If we have this model, you can tell me the coordinate, exact coordinate in space and in time. Just put a pin anywhere on this map, and then you can have a prediction. So this is why we say pin is mesh-free. And another challenge about numerical method, this is for application in real life when we do have training data. Just now we mentioned that we want pin to both fit to the training data and we want it to obey physical laws. So numerical methods, typically they come from the physical laws and they strictly obey that, but it cannot do the task of incorporating the noisy observed data. So this is what I mean by noisy observed data. For example, I have this exact solution of a harmonic oscillator on the left, and on the right, I have a version of it with noise injected. So you can imagine that numerical method would not be able to exactly reproduce all these noises. And if we use a neural network, on the other hand, that doesn't have physics embedded, if we don't regularize it very carefully, there's a risk that it will overfit to explain the noises, but then losing the real physics behind it. So with pin, we can try to achieve a balance that we can fit to the noisy data, even if the noisy data is also sparse. So let's say if I don't have so many points here, if I have like 10 points somewhere in this curve, I can still try to give this pin some useful information because it doesn't only use these data, it also uses the physics. And because we're working with a neural network, it's also good to have regularization to avoid overfitting. So we still have that benefit in the typical neural network. The fourth challenge I want to mention about numerical method is that sometimes we need to solve a different kind of problem that we call inverse problem. So what is an inverse problem? We have to compare it with a forward problem. So far, we have been talking about simulations. Those are the type of forward problem. It means that we know about the system, and we know the input, and we're trying to predict the output, which are the physical quantities or the training data that we are observing, hopefully the same thing. So we go from model to observables, and we assume that we know the physical properties of the system. So in a water dynamics situation, we will assume that we know that the density is 1. We know that there is a certain viscosity, and we know that either we put external force or maybe we didn't. So we know all these things about the system, and we just have to basically either follow the model, the PDE, or we can follow the pin to predict things like velocity, predict pressure. Those are forward problems. And the inverse problem is that we don't know some things about the system, and we're trying to infer these unknown parameters or inputs based on our observations. So here, that's an inverse problem. So you can imagine, for example, I have observations of velocity and pressure of this liquid, but I don't know what this liquid is. I'm trying to find out whether it's water or whether it's mercury based on the observables I have. This will be the inverse problem. And typically, how do we solve these inverse problems? You can imagine that you're basically trying different combinations of the parameters. You're making different guesses about the system and see which one matches the observables more accurately. But you can imagine that this would be very expensive because every time you guess a set of parameters, you're going to have to do the forward problem again. And then that is just multiplicative. So it's often very impractical. But the advantage of pin is that we can fit forward and solve forward and inverse problems using the same framework. Basically, as we train the neural network, we also at the physical parameters that we want to learn. So the neural network architecture has a bunch of model weights. Those will be learned in every epoch. At the same time, in every epoch, we also learn, for example, about viscosity, about density of the liquid. So there's no need to repeatedly solve the forward problem. We can do them in one framework. And later on in the hands-on tutorial, we will see a demonstration of how we solve the inverse problem. Yes, please.
Can it be pictured with the same principle like supervised learning and unsupervised learning? That's supervised for the forward problem and unsupervised for the inverse problem. Can it be pictured like that?
Great question. I think it's not exactly the same in my mind because supervised, unsupervised, to me, that means whether our measurements are labeled, our outputs are labeled, whether we have a good match between the model input and output. So with the inverse problem, sometimes we are looking to infer the input. Sometimes we are looking to infer the parameters about the system. So I think it's not entirely the same. And I think hopefully with the hands-on tutorial that we can see the difference here. I think with unsupervised learning, my idea is that we sometimes don't have the label, which is the output. And here, even in the inverse problem, we still do have the output. What we don't have is that the model is unknown. Yeah.
Okay.
Yes. Oh. Okay. It might be recording, but I will speak louder. Is that going to work? I'm sorry. Yeah, and thank you for asking questions. I will speak louder also. And here I want to show a brief example of how PIN is actually used in research, especially in hydrology. So here they start with a complicated topography. They have measurements at the inflow and outflow. And they use the Navier-Stokes equation or its variation again. And the output is that they can simulate the water depth around this river. So this is essentially a forecast of how this river is going to flood under excessive precipitation. And here we can pause for a moment before we go into actually learning to train the pins. If not, we can go right in and feel free to ask me questions at any point. Okay, so I promised that we talk about PDE. And here I will say this is a typical general form of PDE. On the left, we have a derivative. This U is what we call a solution. This is implicitly represented by a neural network, or in other words, the output that we saw just now. And the derivative has that output on top. On the bottom, it has the coordinates, which are either time or space. So you can imagine this might be either one-dimensional, it's only time, or it might be a two-dimensional coordinate system, it's x and y axis, or it might be a 3D problem with both of the dimensions in space and also time, or it might be even higher dimensional. So we have this derivative on the left, and we also have a function. This n is a function parameterized by theta, and also accepts the solution, which are u. So this function essentially predicts that at a given time point, you have the parameters or system properties. You also know the state of the system. For example, it has certain velocity on the x and y direction. It also has pressure. And how do we predict that the system will change? For example, how the velocity on the x and y axis will change over time. So that's what this equation is trying to do. is trying to predict how this system is going to change given its current state and also given the property of the system. And here, this is a Navier-Stokes equation that I showed just now. Let's break this down and see how it fits into the general form of PDE. So on the left, we have this du over dt. Du is the velocity. This is actually a vector because we can consider velocity on x and y and z dimensions, right? So this u is a it's a vector with 3 components. And we can look at the derivative of du over dt. T is time. It will equal this whole thing on the right divided by the density. So imagine you move the density to the right-hand side of the equation, and that will look exactly like what we have here in the general form. So the parameters in this are density and viscosity. So this is how this function takes in these parameters. But we also have these things, the triangles. Here, the first one is a gradient of pressure. This gradient of pressure is actually how pressure changes over x1, y, and z dimensions. So here we use this triangle to denote this pressure gradient. So you can see that, yeah, this n is a function, and it can have these elements of more derivatives. We can have the u. We can also have derivatives of u on the right-hand side. And this one, the second component, it actually has a Laplacian. So this Laplacian is actually a vector of these things added together. So it has 3 components. Each component is 3 derivatives added together. So you don't have to know about the exact equation, but I wanted to show you that what this right-hand side consists of. It consists of the parameters. It can consist of both the solution itself or the derivatives of the solution. And here you can see that I have, in this one equation, I have derivatives of du over dt. I also have du over dx over dy over dz. So that's a lot of dimensions. So usually I need more than one of these PDE. For example, I need at least 3 of these to get a good sense of the system.
Question.
Yes?
You know what U is, but what are V and W?
Oh, yeah. So sorry, I forgot to explain that. So this U is a vector. It contains u, v, and w. Those are the velocity, but on different directions, on x and y and z direction. Yeah. So we'll use a similar notation in one of the exercises in the afternoon. And in that case, we have u and v, which are the velocity on x and y directions. OK. So what do we do with this PDE in the pin? We can solve 2 kinds of problems. One is that if we know theta, which are parameters, the viscosity and the density, we know them, and we want to know what the solutions or the physical quantities are. So that is a forward problem. And sometimes you hear different names. We sometimes call that solve the PDEs. So when people say, I solve the PDE with pin, that's what we are trying to do. We know something about the system, and we are trying to derive the physical quantities. And another thing we can do is that we find the combination of theta that best describe the observations. That is called the inverse problem. Or sometimes you hear different names like learning or system identification, but they all refer to inverse problems. So here, the general workflow of pin goes like this. We'll start with input, which are coordinates in space or in time, or both. And we'll pass it through neural networks. And then we'll predict the output with the neural network. So far, it's not very different from what you learned in the past sessions of this summer academy. the interesting thing is that with the output, we can calculate the derivatives. For example, we can calculate a derivative of this u over x or over t. We can also calculate higher order derivatives. And this is done with a mechanism called automatic differentiation. And this is going to be really fast and easy, and we are going to implement this with one line of code in the tutorial later. So after we have the derivatives, we're going to calculate our loss function. In PIN, it will typically consist of these 4 elements. You might not have all of them all the time, but they fall into these 4 categories. So we will have the data loss, and this is how our physical quantity output compare with our observations. We are familiar with this one. This is no different from the usual neural network. But the different ones are, first we have a physics loss, or we can call it PDE loss. This is when we plug these derivatives into the PDE. What residuals does it output, or like how different it is from our PDE? And we take those residuals together, and we calculate a loss. And we're going to do this later. We also have other 2 components, boundary conditions and initial conditions. So boundary conditions are, for example, I know that I have a river at the gate, at the inflow. I know the velocity of the water. I also have, I know the velocity at the riverine when it enters the sea. So these are boundary conditions. At certain points, especially the start and end of this domain in space especially, or in time. For example, I know that after 10 days, there will be no more flooding. So this type of predictions, we do know how to do them very well. So these are the boundary conditions. We can directly see whether the output fit our understanding of these boundary conditions. We can also have initial conditions. So initial conditions is defined a lot more narrowly. It's literally when t is 0. How do we expect the system to be? We know the starting state. For example, for a river, we know that we start simulation from a point when it's not flooding. So that's the initial condition that we are expecting. So these 4 terms will each give a loss, and we'll take them together. We'll summarize them. Either we add them together directly, or we apply a weight lambda and then add them up. So this loss function will help us optimize 2 things. One is that we can optimize the weights in the neural networks. And the other one is that if we are working on inverse problem, we can also optimize the physical parameters at the same time. So this one doesn't show the physical parameters, but if you do have them, they will be somewhere here, all right, somewhere here, together with the neural network, but not connected. It will separately feed into the calculation of physics loss. So you have the physical quantity, you also have the physical parameter. You calculate the physics loss with both of these together. So that's the way that the physical parameters enter the system. You update it together with the model weights, but it's not directly embedded within this neural network, if that makes sense.
So could I just understand your
Yeah.
theta in mu?
Mm-hmm.
Mu here is not viscosity?
So in this case, yeah, sorry, I didn't update this figure. My understanding is that we update 2 things. We update the theta that we just mentioned. We also update these model weights sigma. So they probably use this figure in a different context. Sorry, I didn't update that properly. Yeah.
So this is just to get the weight of the neural network at the end? Is that
Right, so if you're working with a forward problem, after this optimization, you get the neural network model weights. Mm-hmm. And then with that properly trained neural network, you can predict, for example, what the physical quantities, velocity, or pressure will be at any given location, any given time. So that's the expected outcome. And if you're working with an inverse problem, you're expected to get both the model weights in the neural network and also the physical parameters, for example, density of the liquid and viscosity of the liquid. Yeah. Okay, we're going to dive into a case study. This is a case called harmonic oscillator, and I say 1D because we are only considering the dimension of time, how this displacement from the equilibrium position changes over time. And this is a forward problem. So we start from here. The problem is such that we have the spring, and it's usually static, but we try to stretch it. We stretch it down, and then we release it, so it will tend to bounce back. But this is a special case of it, that it's a damped harmonic oscillator. It means that it will bounce back, and it will try to extend again. It will bounce back, but on a little smaller magnitude. So if we plot this displacement from the equilibrium position, we will get a curve like this. So we'll start with a very large positive number because we stretch the spring. And then the block at the end of the spring will go back to its equilibrium position, but it will overshoot. That's when it goes negative. And then it will oscillate. Eventually, it goes back to equilibrium position, and this x becomes 0. So this system has a few parameters that we do know about. For example, the mass. We know the mass of the block here. So this determines the inertia of the system. And we also know the damping coefficients. So for example, if there's air resistance, we know that. And we also know the K, which is spring constant, or in other words, how stiff this spring is. If this spring is very stiff, it will overshoot a lot more. So it would tend to restore the spring very rapidly. And this is the PDE that describes the dynamics here in this system. So here we have 0 on the right. What do we have on the left? We have the first and second order derivative of x and also x itself. We also have the parameters m and mu and k in this case. So what are we expecting? What should this ideal pin do? So this ideal pin will give us a set of x at any given time point t, and at any given time point, we will hope that the x and also the derivative, first and second order derivatives of x over t, when we plug them in, these three elements added together will be exactly 0. That's the ideal situation. But you can imagine that when you're first starting to train your network, maybe in the first epoch, it will be different. These three elements added together, it will not be 0. It will be some kind of positive or negative number. So we're going to penalize that, and we'll try to get the model to predict the sum as 0. And I want to remind us here that this is not a PDE. It's actually an ODE, what we call an ordinary differential equation. It has a very similar structure. So sometimes you can even consider a special case of PDE. Because PDE often involves derivatives with respect to multiple independent variables. Like in the Navier-Stokes equation just now, we see on the left du over dt. We see on the right du over dx or over dy or over dz sometimes. But in this case, we look at the derivatives. We only have dx over dt, so only dt on the denominator. That means that we only are working on a one-dimensional problem. This one equation can tell us almost everything about the physics of this system. We don't need a set of equations. So that's the characteristics of ODE compared to a PDE that we usually have. All the different derivatives, different independent variables, and we usually need multiple of these PDE to figure out the system. So just now I mentioned that this is a 1D problem. It's very simple, and we can even derive the solution analytically. So by deriving that analytically, I mean that if if I can write this function that I know my time, and I can predict x at any given time directly by calculating this with the parameter of the system that I know and with the time, that is very straightforward. That is the exact solution. So we are very lucky in this case that this is not a complicated physics problem. And if we plot this x over t based on this exact solution, we actually get a really good trajectory. This is the perfect trajectory that we are expecting. But the thing is that not all the PDEs have exact solutions. The Navier-Stokes equation that I have just now often doesn't have the exact solutions. So even though this is a simple case, it is just for us to demonstrate how we can use pin. But in real life, yeah, you might wonder, do we ever need to use a pin on harmonic oscillator? We probably don't, okay? So this is just for demonstration. So we talked about numerical method at first. We talked about so many challenges of it. Let's see how we will actually do it in this case. So numerically, we will simulate the changes at each time step. We will calculate the force that determine how the spring will go. We will calculate, for example, the spring force that pushes this spring back to equilibrium. We will also calculate a damping force that prevents the system from going back to equilibrium. So these forces together will be our F. That's the net force that this block at the end of the spring receives. And we also know the mass of this block, so we can calculate acceleration. And with the acceleration, we multiply by the increment of time. For example, over 0.001 second, we can calculate how much this velocity is changed. And we add that to the existing velocity that we know from the previous time point, and we know the updated velocity. With the velocity, we can again update the position of this block. So on the two panels, on the left, I have this simulated over time step of 0.001 second. So I do a very fine grid solution. At any 0.001 second increment, I calculate these 4 steps, and I get the updated x. So you see that the exact solution and numerical solution, it's basically one line. It's the same, right? So numerical solution, it can be very accurate, but it also is very time-consuming because I have to simulate over thousands of time steps. And then on the right-hand side, this is also from my numerical simulation, but I did it over 0.1 second time step. So you can see that my orange line, which is numerical simulation, is very jagged. It's not very good. All right, so this numerical solution, it can do the job if we simulate at very fine steps, but then it can also be quite off if our grids are not fine enough. So this goes back to the challenge. How do we generate the mesh, or how do we generate the grid that's good enough, that gives us good performance on the outcome? So after looking at the numerical method, we see that it's probably very computationally expensive. Sometimes it's not accurate, as we have to take care in generating the mesh. And now we are going to see another solution. What if we use a neural network? A neural network here without the physics, okay? Here, the loss function for a neural network will only contain the data loss component. No PDE loss component, no initial condition, no boundary condition, only data. Okay, this is what we are familiar with so far. So we only look at how well the network fits with the provided data points. This could be either from the observations, or if you do experiments, you can get them from experimental data too. So here, I know the exact solution, so I don't have to observe. I just grabbed 10 of the points on the initial part of this system. Okay, so I pretend that I know the exact x at these 10 points of t. Okay, these are my training data. So how would I actually fit the neural network? we'll usually predict the solution at the known data points. So for example, our neural network is called model. We know the given time point, these 10 time points, all right, either 0 or 0.1 or 0.2. We'll pass these time as input through the neural network, and we'll get a series of predictions. So these are what I call XPred data in the code. And then we're going to take these predictions and predict them with the observations, which I call Y data. So you see I calculate the difference here, and I take a square, and I take a mean. So this is the usual MSE loss. Basically, I take all the residuals, I take their square so that I ignore the signs. Either positive or negative residuals are considered not very ideal, so I penalize them both. And I will summarize them with a mean to get one number of loss, how much I should penalize this neural network. So this is what we have been doing with neural networks so far. And let's see the performance of these neural networks. OK, so the exact solution is in gray line, and the neural network prediction is in the blue line. So you see that after training 5,000 steps, I do see that it fits the training data pretty well. It passes through all of the 10 points. OK, but even if I increase my training, you don't see it predict the end part. It cannot extrapolate beyond the training data. So here we see how this neural network is falling short in the areas that do not contain training data. Or in other words, it's not figuring out the physics behind it. If you, for example, using a human eye, you see this oscillation, you probably have a sense, OK, this might be a harmonic oscillator, and it's going to keep oscillating until it reaches equilibrium. You probably have a guess that it's going to do this behavior like the exact solution. That's because you have learned them in physics. You have some knowledge that help you predict what is going to happen beyond the training data. But the neural network, at this point, it doesn't know. So that's why we are going to use our pin to incorporate these things, physics, and maybe sometimes when available, we have initial and boundary conditions. So hopefully this will allow us to build on the sparse training data, or even sometimes no training data, but still predict the system reasonably well. So the neural network setup in a pin is not too different, but I want to point out a few unique things. So the input in a usual neural network can contain a lot of different environmental predictors or the neighbors' values. But here, for a pin, we typically just use the temporal and spatial coordinates. You don't have to use the full set of them, whatever is available. And the output is usually the latent solution. And the architecture of this pin is typically pretty shallow. Sometimes in neural networks, we use a lot of layers, a lot of hidden layers, very deep neural network. But for pin, it's typically very shallow. And it's also, each layer tends to be moderately wide. So these combinations, shallow and wide layers, have proven to be quite effective in training pin. And because if your physics are good enough, and having a shallow layers will be sufficient, and it will make your compute faster, so why not? And sometimes in neural networks, we use dropout or we use batch norm. But in pin, we typically don't do these two, because remember, we have to use automatic differentiation to calculate those derivatives. And these actually rely on the neural networks architecture that is very complete. So try not to use dropout or batch norm, because these will interfere with the derivative computation. And the physics that you get from that is not going to be correct. And another thing to note is that we sometimes use activation functions in the neural networks. For example, sine, soft plus, those are all fine. But we do need our activation to be smooth. So this, again, comes back to the derivative computation. If you have a non-smooth activation function, for example, ReLU, basically the automatic differentiation cannot calculate the derivative, especially at the point that it becomes non-smooth. So that is not going to be great. And the optimizer, usually we start with an atom. In all the tutorials today, we use atom. You can also follow up atom with a more fine-tuning optimizer like LBFGS. That one is optional, depends on the problem that you're working on. Okay, so yes, please.
Could you say a little bit more about why the network is shallow and wide, or moderately wide? What is the trade-off generally? What do you achieve usually if you have a deep network versus a wide network?
That's a great question. Yeah, I think I'm not an expert in this, so I cannot answer that question, but maybe give me a little bit of time to think about it, and I'll try to answer it in the next session. Yeah, okay, thank you. So this is starting to be the meat of this lecture. So if we take away anything, it will be in the next 5 slides or so. So physics laws. It ensures that the network solution satisfies the governing equation. It can be a PDE or it can be an ODE in this case with a harmonic oscillator. So this will be our ODE. So the first step is that, remember just now with the data loss, we predict the solution at any given time t. So here we are going to do that too. We want to have a set of labeled data. Basically, we know the input and we know the output. Okay, so how do we predict the solution from the neural network? The important question is that, where do I even predict from? What independent variables do I need to predict the solutions? In the previous case with training data, we are pretty clear. With the training data, they are sampled at these 10-time steps. But for physics, nobody's going to tell us where we can sample them. So we have to decide that ourselves. We call these independent variables we choose to predict the solutions, we call them collocation points. And they are the points in the domain where we evaluate the residuals of PDE. So you can imagine you can infinitely sample the domain. That will get your PDE more accurate. That will get your PDE very well represented in the pin. But usually you don't want to, and it's not possible to cover every corner. So you have to do some kind of sampling, usually. There are a few types of collocation points. For example, this is a different problem in another tutorial that we're going to see today. Here we have 2 dimensions. One is time, and one is space. So to clarify, this is not the harmonic oscillator problem. I'm just using this to demonstrate all different kinds of collocation points that we can see. So these interior points here, they are randomly sampled here, but you can also use uniform sampling or adaptive sampling within the domain of a reasonable time frame and a reasonable distance that you want to make predictions over. So the interior points, they differ from 2 things. They differ from the boundary points and the initial condition points. So what will be the boundary points in this case? It will be when x is 0, these green points. So when x is equal to 0 means that, for example, that's the start of this space. And we know something about the start of the space. For example, that's our where we place an electrode, and that's the surface of the electrode. And we're trying to predict the concentration. We know how it's going to behave on the, we want to predict the concentration of some kind of ion. We already know how it's going to behave on the surface of the electrode. Okay, so we have knowledge about that. And that is one of the boundary conditions that we can impose. So we have these boundary points. And the other boundary points is, for example, x at value of 6. So this could be some place that's far away from the starting point in space. we know that, okay, there's probably not much going on at x equals 6, so I can safely assume that it's 0. So that kind of assumption is a boundary condition, and we can impose that kind of assumption by putting these boundary points. And what are the initial condition points? They are literally when t is 0, how this system behaves like. So we can have these blue points with t equals 0, but x randomly sampled. So these will be our initial condition points. And the interior points are the points within this domain, but they have t that are non-zero, they have x that are not 0, or 6 that are somewhere within this domain. Okay, so that's the concept of collocation points. The point is that we sample relatively comprehensively throughout the domain where we know they obey the physical law that we impose, and we are going to use these points to predict the output. So when we are writing code, we might see something like this. We want to, coming back to the harmonic oscillator, we want to have a series of time points that we make predictions over. And we can do this, for example, this is a uniform sampling. I want to, let's say, predict 30 points, at 30 points in the domain of 0 second to 1 second, okay, because I don't really care about how it happens after 1 second, but I do care about how it happens between 0 and 1 second. And I generate 30 points. And here, this number, how many sample points, how many collocation points that you generate, that is up to you. You can play with it. If you want physics, if you want this model to represent physics even better, you give it more points, basically. And note that here, after we generate these points, we need this required graph true, because later we are going to take derivatives with respect to time. So if we know that our collocation points is going to be involved in the computation of the derivatives, we want to do this required graph true, because we need the gradient, basically, with respect to time. And then we will pass this t-physics, these collocation points, through the model, which is a neural network, and we'll get the prediction about the x. So here we have predicted the solution from the neural network at collocation points. Step 1 is done. We have pairs of x and t. That's great. And the second step is that we compute the derivatives with automatic differentiation. And here, a little bit more about automatic differentiation. It computes automatically the exact derivatives of functions, like neural network outputs. Because neural network, if it's a very shallow and very wide neural network, it behaves a little bit like a linear function sometimes. You know, for linear function or a polynomial function, you can pretty much compute the exact derivatives. And similarly, for this neural network, you can compute the exact derivatives too, because we know how we got this u from x and t exactly. And we can calculate with respect to all of the input. Basically, if we do automatic differentiation, it will give us u over dx and over dt, whatever input that we give it. And it does this automatically by applying the chain rules through the computation graph. So the model needs to have the structure very clear for automatic differentiation.
Could I ask a question?
Yes.
Here?
Mm-hmm.
The collocation points that were chosen,
Mm-hmm.
are they part of my input or?
Yes, they are part of the input. Yes, you are very right.
So essentially, you are trying to make a good selection of points so that the lateral solution that you get is of high quality.
Well, yes. If by high quality, you mean that it represents the
physics.
Yes.
Because if you miss out on the boundary condition and the
Right.
initial values, then you will not get a
Right.
solution that U is not of good quality.
Yes,
So-
exactly.
So, because I find it confusing when you say predict.
Mm.
Predict would be the user's choice. I want to know the velocity at this point in the server. Or
Yeah.
I want to know the position of the spring at this point. That should happen much later.
Yes, yes, you are exactly right. So the prediction that the users do after we train this pin, that's
from
another, yeah. So the prediction that we mean here, it literally means we take these collocation points, we feed it through the neural network, not even the pin. We feed it through the neural network component of the pin, and it will then give us the neural network prediction of it. Yeah.
And here, all the loss calculations are already done in this layer. Because how is it able to make a prediction? You have to do some objective function has to be defined.
Right, we haven't got to the loss function calculation yet. So far, we have got the predictions, we have got the derivatives, and with those, we can calculate residuals, and then we can calculate loss function. And then we can calculate the loss. With the loss, we optimize the neural network.
But how can it arrive at any u otherwise?
Pardon me?
How can it arrive at the Latin function u without any measurement of what it's trying to optimize?
Let me try to understand that. Okay, so if we are just starting to train, the neural network is probably a very bad one. So we'll feed the collocation points through this pretty bad neural network. It will give us bad predictions, probably. By bad predictions, I mean that if you plug in the derivatives, if you plug in x into this equation, this is not going to be 0. So it's going to end up with a positive or negative number, and that is our residual. Our residual, we take that, we summarize that either with MSE or some other function that we choose, is going to be our loss. And we try to minimize that loss as we train the neural network. And after the neural network is updated sufficiently, at that point, if you pass T physics over that neural network again, it will give us pretty good x, which when you plug in x and x derivative, it will hopefully give you 0. Does that clarify things?
Maybe, if you can show me the next slide, I
Yes.
can properly frame my question. So my question is,
Yeah.
If you look at the sigmas which are in blue and u, is that part trained separately and then the output pushed further, or you go all the way to the end and then?
Oh, great question. Yeah, all the way to the end, all the way to the end. So our loss function will kick in after we calculate the derivatives, and at that point, we come back and optimize, update the model weights. So when we code them, we will have a neural network, but we will wrap it in pin. And in our training loop, we'll use that pin wrapper with a neural network component in it. Yeah.
Okay.
Thank you. Thank you for the clarification question. Okay. So we know that we want to use automatic differentiation, and I want to briefly show you the code of how we can do that. The function we use is called, here I use a PyTorch framework, and there are other frameworks out there, but I personally feel like PyTorch is very popular. It might be handy in a lot of cases. PyTorch has this function called autograd. This is its function for automatic differentiation. It will take 4 arguments here. Outputs and inputs are the things that are on top and bottom of these derivative. So if I want to calculate dx over dt, I will have x on the top, and I'll have t on the bottom. So note that these are exactly what I got from the prediction step 1. I predicted x over my collocation points t. So those will go into my output and input. And then it will need a third argument called grad outputs. Basically, this asks us for a dimension of the dx over dt that we're expecting. And usually, we will want this dimension to be exactly the same as the output that we are expecting. Basically, I mean that at every given collocation point, I want to know the derivative at this collocation point. So it's typical that you do a torch 1 slide, and you put in the output exactly here. So this will make sure, let's say if we have 30 time points as collocation points, I will get 30 predictions, and I will get 30 dx over dt after I pass it through this function. And the last argument is create graph equals true. So we use this when we want to calculate higher order derivatives. For example, here we have dx over dt, and then we also notice that we want second order derivative. And that second order derivative basically is the first order derivative, we take derivative again over time. So we want to build on what we already have and take derivative again. So we require this create graph to be true so that later we can use the output and take derivative again. So let's call this dx over dt, we call it dx. And then let's see how we can use this dx to calculate second order derivative. So here, the input is the same. Output, instead of having the x, we will have dx over dt. And the graph outputs, again, we want it to be the same dimension as the output here. So we generally have the same output and the same argument here. So here, it doesn't really matter if I want to create graph because I'm not calculating a third order derivative, but it also doesn't hurt. It doesn't make a great difference at this point. OK, so now we have both of the derivatives that we need. And now we are ready to calculate residuals and loss. So like I said just now, if the model, the neural network model, is very well trained, then we expect these three terms added together to be exactly 0. And if it's different from 0, that means, OK, it's not very ideal, and we want to minimize that. So this left-hand side is going to be the residuals. If the right-hand side is a 1, we will, hypothetically, if it were 1, we'll have the left-hand side minus 1 to be the residual. But it happens to be 0, so we'll take the left-hand side, these three components together, to be the residual. So how do we calculate that? We have second-order derivatives. We know the m. That's the first component. We have first-order derivative. We know the mu. That's the second component. And then we also have predictions of the x. We know the k. So we know everything here to calculate the physics residual. And here we want to minimize this. So we will take this physics, we'll take a square because we want to penalize either positive residual or negative residual equally. And we'll take a mean. So this is the usual MSE loss. And you can feel free to change the MSE loss into any other different loss, depending on the problem that you're solving. And note that I also apply a weight here. So for example, in this problem, I think I just want to gently nudge it into the direction of the physics, because I also have training data. I want this balance between training data and the ODE. So I apply a weight here. And this is a pretty small weight. It's like a gentle nudge towards the physics. Sometimes if you think, OK, my data are really bad, really noisy, they probably can be wrong sometimes. But my physics, I have very strong faith in it. So you can put more weight onto the physics loss. So later, after the break, we're going to talk about how this loss weighting can be pretty complicated, and it needs a lot of trial and error sometimes.
Good question.
Yes.
So, to make sure I understand this, because this is a for problem, right? So you
Yes.
take what parameters and you k
Right, yes. In an inverse problem, you are exactly right that the m and mu and k, or like subset of them, might be unknown. And like we said, we will still calculate starting with the very bad parameters. And then we'll generate the loss. If it's bad, we will come back and optimize. We tune both the model weights of the neural network, and we also tune the unknown parameters. Yeah. So you'll still have this even in the inverse problem, just that in the inverse, we will want to update them. Yeah. Thank you. There will be extra step, but mainly if in the inverse problem, you have to specify in the neural network that I also want to carry some of these parameters. I want the model to update them too, just that it doesn't, it's not in the same chunk of code with the neural network layers, if that makes sense. So there will be additional lines of code to specify we want to update them. Yeah. But you'll still have at least these 2 lines. Okay. So just now we talked about weighting. We can do a vanilla weighting is that for initial condition, boundary condition, PDE, residuals, we calculate their MSE and we simply add them together. But we can also multiply these MSE by a factor, and then we calculate the loss that sums up the MSE multiplied by the weight. So you can see this weight will help you balance which one you think are more valuable or which one you would want the model to conserve more. So you can say that the initial conditions might be really, really important, so you increase the weight from this, or you think the PD is really important, so you update this. Or sometimes we update the weight adaptively to achieve a best performance in prediction overall. So there are a lot of fancy tricks that we can do with the weighting here. Okay, so we talked about PD loss, and I think at this point, you have learned the most important thing about PIN. It is over, and the rest are relatively easier. Yeah. And loss function, we can also have the initial condition loss. That will ensure the network solution satisfy the initial condition basically at time 0. And this is not always available, but sometimes we do know. So what do we know about this spring at time point 0? I know that I actively stretch the spring for 1 unit in space, right? So I stretch it, and then I release it from there. That's my initial condition. It has 2 things I know. One is that the displacement at time 0 is 1. I stretch it. The velocity, dx over dt, is 0 because I simply release it. My hand is not giving it external force. It's not that I stretch it and I also push it. I didn't do that. So I know that I stretch it and I release it. So these 2 will describe the physics of my movements at the initial condition. Oh, sorry, I wrote wrong here. The velocity is 0. It shouldn't be the acceleration is 0. Acceleration shouldn't be 0 because there will be the spring force and also the damping force. I will update this in the slides. Velocity is 0. OK. So we'll do a similar workflow. We'll still predict the solution at collocation points. Here, the collocation point, I shouldn't call it points because it's literally just 1 point. Time equals 0. Right? So I want to predict the solution at the initial condition. To us, it's very obvious here that the prediction from the neural network from at time equals 0, it should be 1. But the neural network, if it's a not trained, untrained neural network, it doesn't know that. It will tend to give us other answers other than 1. So we will still have to impose that constraint. So here, our T0 is really just a tensor with 1 element 0, and we'll pass it through the neural network model, and we get prediction at 0. And later, we can use that to see whether it's equal to 1. We can also calculate the derivatives at the initial condition. So we know that it's 0, but the neural network doesn't know, so we still have to calculate this. Same arguments. X prediction at 0 is going to be the output. Time 0 is going to be the input. it doesn't matter if we create graph, but we do want to make sure that the output has the same dimension as our collocation point and our prediction, which is just one element. We just want one value of derivative at t equals 0. Yes, please.
Two questions.
Yes.
So is the torch ones essentially saying that we are not taking partial derivatives? Is that the idea?
So the torch ones, like, this means that I give it a series of ones that has the exact same dimension as x pred 0. So it's to tell this function, my derivative is going to have the same number of elements as my output, basically.
Can you tell me something about the situation where I would want it to be different?
Where we want it to be different. Sometimes I think if we have a series of derivatives, but we specify that the dimension of output is 1, it might be a summary of all the derivatives. I'm not sure if my understanding is correct.
Last, something where you're summing things up?
No, it doesn't do that, yeah. Me personally, I haven't seen a case that I don't want it to be the same. Yeah, I can look into that more.
And what is it capturing with the 0? The first component, the very end of the code, very end.
Oh, this one.
Yes.
It takes the, let me think. Yeah, that's a great question. I never really thought about this. Yeah. By right, it takes the first element, but I can look into what the other elements are, and then I can figure it out. Yeah. Okay. So we have two equations here that we want to satisfy. One is that we want x prediction to be equal to 1, So we have this as our residual. The other is that we want the velocity to be 0, so the velocity is our second residual. And for both of these residual, we will take the square, and we'll add them together. And then here, I'm not taking the mean because I literally only have one time point. But if I hypothetically have multiple initial condition collocation points, I will have to do a summary here also, maybe with torch mean. And here I again impose a small weight to gently nudge the neural network to the direction that satisfies the initial condition. So now I have summarized the initial condition residuals, and I have got this loss term. This is also just one number. We do not have a boundary condition loss here exactly. So if we hypothetically had boundary condition, it will be, yeah, it doesn't really make sense here because we only have one dimension of time. So if we think about another case study, if we have, that has both space and time dimension, then you can specify, for example, when x equals 0, what this system will behave like. When x equals to a known number, maybe a large number, that you know is the end of this domain, what would be the system like? So we don't have this term in this case study per se, but the implementation is very similar to that of initial condition. So instead of having t equals 0, you will have x equals 0 or x equals 100 or something. All right, so let's see the performance of this pin. So now we added physics and see how our training performance improves so much over training steps. Actually, by the end of our training, the neural network prediction is so good that it can recover the exact solution even when we don't have the training data available. And here, these green points are the collocation points, or where we predict the physics at. So remember, we sampled 30 points within the domain of 0 second to 1 second, and we made prediction. So these are where we evaluated the PDE residuals, and then we calculate the PDE loss. So you see, even though my training data doesn't have a full coverage, my physics loss training locations have a pretty good coverage. So that kind of ensures that even in the area that I don't have training data, my neural network will behave in a way that follows the physical laws that we specify. But I do have a warning here. PIN sounds so good, so fascinating, but it's not foolproof all the time. So especially in the cases of extrapolation, we say that it's good for extrapolation in the previous graph, like when we don't have training data. But if we say we extend beyond time point 1 and we predict how the system is going to be like, there's a good chance that the PIN predicts it well, especially compared to a neural network. But there's no guarantee that it will still perform well even beyond this point, especially if we compare to a numerical method or to even analytical solution. So we say PIN is good at extrapolation to an extent. We can't say that, oh, PIN is going to be as good as the golden rule of exact solution, even beyond the domain, especially that we train it on. Okay, so here, I want to say, in some cases, there's no guarantee. So in the left column, we have the simulation, or you can consider this as the standard. This is the best outcome it's supposed to be like. We have 3 different scenarios, and we try to recover them with different models. The baseline neural network, if you compare it to the simulation, baseline neural network that doesn't have physics is pretty bad, especially with this very complicated situation. And how about PIN? There are here they experimented 2 different variations of PIN, I think with different constraints imposed. They're both PIN, but we just implemented slightly differently. We give it different constraints, we give it different loss terms, but look how the performance might differ. The PIN second one, it does quite bad in recovering the simulation in some cases. So this is to say that even if we have a PIN, we still have to be very careful and do a lot of evaluation whether our PIN is really recovering the physics. There's no guarantee. Okay, I think this might be a good point to pause, and before we go into the second case study, we can answer some questions. Yeah.
If we cannot predict what happens in pain in the future, can we determine the threshold where we can get a reliable information with PIN?
Yeah, I think that's a very good idea, and I think that's a good practice to see how much it can extrapolate. So I think in practice, if you want to figure out how much it can extrapolate, you can train on part of the domain and see how it performs on the untrained part of the domain, see if it still recovers the exact solution or the numerical simulation. I think in the cases where extrapolation is necessary and expected, that's a good practice to do. In a lot of cases, we might not need extrapolation per se. For example, if we have a nuclear reactor, it's a container, and we want to know the dynamics inside, for example, the temperature at any given point in this nuclear reactor. We don't exactly have to extrapolate beyond this container, so as long as our PIN accurately reflects the physics within this container, in this domain that we define, that is sufficient. So I think PIN would be a good use case in those, but if we want to extrapolate, it performs better than neural network, but we still have to be careful by doing the evaluation, maybe on the untrained portion of the domain, I think.
Okay.
Yeah. Especially we can compare that extrapolation to maybe neural network, baseline neural network without physics. But I would say eventually, if we know the physics, that is still the golden rule. We will have to compare our extrapolation to the physics. If we have to do simulation over those unpredicted domain, I think it's worth doing. It will be some computationally expensive, but I think it's necessary to do them. Yeah, thank you. Yes.
So in the sampling methods, you mentioned we'll be using random sampling. So the collocation points that we'll be selecting will be from the random sampling, right?
Yes.
But the collocation points wouldn't be randomized. Would they be randomized? Like
You mean their order might not,
So
they're not
we
shuffled?
have,
Yeah.
say, a uniform distribution. So will we be selecting the collocation points randomly from the uniform distribution?
Ah, great question. Like, yeah.
And the second question would be, if our sampling itself is randomized, would we be randomizing the collocation points within a randomized sample generation?
I think I kind of, yeah, that's a great question. So we can, yes, on one layer, random sampling, it means that mainly in this domain, we can sample get the collocation points randomly. But once we get these collocation points, what do we use to train the model? In this case, we have 30 points. We can use them all. But in another case, for example, the complicated collocation point graph, there were maybe hundreds or thousands of points, and then it will be very slow and overwhelming to train with all of them. In that case, we can do a sampling. We use part of them in every epoch. We draw a random sample from all these collocation points. Yeah, that will be totally viable. And actually, in the second tutorial today about cyclic voltammetry, I think we do have a random sampling because there are so many collocation points. Yeah.
And one more thing is, after we compute the loss function, we do back propagation, right?
Yeah.
So when we do the back propagation, do we train the model at the collocation points, or do we back propagate the weights randomly again? The model remembers okay, these are the random samples. So when it back propagates the loss, it will be applying only to the sample points. Will it actually remember? Do we use LSTM?
No, it doesn't have that kind of dependency. So the model, after we train it, is not aware of which points they were trained on. It will not remember that.
It actually back propagate the loss because it needs to adjust the loss, right? So that it improves its prediction.
Yeah.
And you said the loss would happen because the residual would be adjusted. The weight would be added to the residual.
Right.
And we are actually calculating the residual at collocation points, and collocation points are actually randomized. So I wasn't able to put everything in one picture.
Either we use all of the collocation points or we use a random sample. The model is not aware of which points it's trained on. It will not carry that information like an LSTM, if that's what you mean. Yeah, and that we will talk about that a little bit. That's one of the drawbacks of PIN, actually. Yeah.
And I think his question is, once selection, once some random points are selected, will it use those in its back propagation, or will it work on a new set of collocation points?
I think in each epoch, it uses one set, and then when it moves on to the next training epoch, it will change a different set.
Okay.
Yeah. Does that answer the question? Okay. Yeah, I think we can have a break here, if that's okay. And let me see what the schedule is like. Okay, I think we'll come back here 10:15. Yeah, and I'll be here to answer more questions too. Okay, everybody, are we ready to get started on the second half of our morning? So here I want to go back to a few of our previous slides to really review the meat of this whole PIN day. If we take away anything that we can use in our code, they will be in these few slides. For example, the core of PIN is that we will generate collocation points. We will feed these collocation points through the neural network model. And then we will compute derivatives with automatic differentiation. In PyTorch, there is a function for this autograd. And then we can also use this to calculate higher order derivatives just by applying this function over and over again. After that, we plug in these predictions and derivatives, and also either our known parameters or our guesses of parameters into the PDE and calculate the residual. Just now, we had a discussion over the break that how can we describe the residual? Does this function have to be in this form? What if it has other terms on the right-hand side? So I would say maybe we can understand residual as the difference between the two sides of the equal sign in this equation. So don't worry if you have different things on two sides. It's okay. You can take the left-hand side minus the right-hand side. That will be your residual. But we usually try to arrange everything nicely, have all the components on one side and just leave 0 on the other side so that we can calculate our residual in a very straightforward way. So we have the residuals. We summarize them either with MSE or something of your choice. And we apply a weight. And here, this 1e minus 4 actually just represents 0.0001. So it's a very small number. We apply a weight to each of the loss term. Could be physics loss, could be initial condition loss. You can apply different weights to them. And this will be a loss. We'll add our loss from different terms, up to 4 terms together. And then that will be the final loss. And we use that loss to optimize either model, to optimize both the neural network model weights, and if we have, then the physics parameters. Yeah, so that is the idea of training a simple pin. So here I want to have your opinion on the order going next. So we have 2 options here. I do have a Google Colab notebook for the harmonic oscillator that we just showed. We can do that. Or we can keep going on the slide deck and talk about another small case study conceptually, and we talk about some challenges and limitations and solutions of applying PIN. So these are the 2 options. First is hands-on tutorial about the harmonic oscillator. 2 is going through slides. We'll still do both of them, just which one do we want to do first? All right, and let me see a show of hands. Who wants to do the hands-on tutorial first before the slide deck? Okay, I have a rough idea. Who wants to go through the slide deck first before the tutorial? Okay, I think we have a pretty good answer, but don't worry, we're still going to go through both of them. So for harmonic oscillator tutorial, you'll find them on Canvas, day 4, then 1.5. Here's the PIN's hands-on exercises. You see I have 3 links here, and then you can click on the harmonic oscillator, and then we'll leave the cyclic voltammetry and fluid dynamics for the afternoon. So we'll do the first one. After you click on this link, you will see, you'll see this Google Colab notebook. Here, the thing is that you can't edit mine, so you have to save a copy in your drive, then you can start to edit it. Yeah. So you'll create a copy that will open up a new tab, and on this copy, you can do all sorts of explorations, basically. And you can also move it to your the folder that you want, if you want to keep it. Okay, so all 3 tutorials I'm going to show today, they will follow this general workflow. I made them the same so that hopefully it's easier when you want to adapt this kind of notebook to your own problem. So we'll start with some basic setup loading libraries, and then we'll look at the problem, including what are the PDEs involved or ODEs involved. And then we'll do data generation. Either we load the observation data if we have them, or we can generate collocation points. So that's what we do in the 3rd step. And then we're going to build the neural network. This is one component of the PIN, right? It's a typical neural network, but it does have the features that we just said. For example, input will be coordinates, and the network is generally shallow, is generally wide, and then no non-smooth activation function, sort things like this. And then after that, we are going to wrap this neural network with a pin wrapper. And this pin wrapper will contain not only the neural network, but also how we calculate the residuals and loss. After that, we are ready to take this pin wrapper, and we actually do the model training. We do the prediction. Yeah, so that would be the general workflow. And now we can focus on the notebook itself. So I really like Google Colab Notebook recently because it does have a lot of Gemini support. So I want to note that before we start, that you can use Gemini in so many different ways here. For example, if you click on this chunk of code, there's a star here. You can ask it to explain code. And also you can activate Gemini here. You can type in with your natural language to say what kind of code you want it to help you write. Yeah, so those are some pretty strong features. I've experimented. They're pretty good. Yeah. So feel free to especially explain code at any point. And to run this, the code in this notebook, basically you push the buttons here. This will run the cell. Usually these cells are pretty fast to run, but if it's very slow, I will let you know. We'll press the button first, and then we will do more talking and explaining as we wait for it to run. Okay. So you can, on your computer, feel free to click through this with me. So let me see a show of hand. How many of us have got a copy of the notebook and have run the first cell? All right, yeah, let me know if you're getting stuck at any point. So we'll proceed with talking about the problem. We mainly talked about it just now. Stretching the spring, releasing it at 0 velocity. And then we know the initial condition. We know the ODE for the system. And again, this is a case that's too simple to use pin for in real life. This just to demonstrate the workflow. I say it's too simple because once we know these parameters, for example, we know the mass is 1. We know something about delta and omega. You don't have to really care about the physical meanings behind this unless you're really interested and you want to read about it. But basically, this delta is a damping ratio. It determines how fast the system loses energy. So this could be driven by like air friction, or if you're putting this spring on the table, it could be the friction from the table. And there's an omega 0 that describes the natural frequency, which is what is the frequency that the system will oscillate without any resistance, without any damping. So you can imagine that how stiff the spring will contribute to this factor. So we specify them already. This is a forward problem. And we can calculate from these mu and k. So we already have m, and you see mu and k in the ODE, so we are going to use mu and k later on. I say this is an easy problem because we know the exact solution. And let's plot the exact solution and see what it looks like. Here I write a function called oscillator. This contains basically a translation of this exact solution. And I want to plot it over the domain of 0 second to 1 second. And this will be how the displacement look like over this time. And in the slide just now, I showed how we can use a numerical method simulating x at each time point. So you can do that. And here I use a time step of 0.01. And I encourage you later after class to play with this and try the numerical method with a different time step. So this will probably give you a slightly different simulation, and you can compare this outcome with the pin outcome. But yeah, this is to show that if our numerical simulation is at very fine time step, we're doing fine. And then now moving on to pin. First, we want to get some data. And here, if you move on to section 3 and run this code, you'll see here we sample 10 time points with their x. So these are the orange points that we know. These are the training data. We intentionally only trained with the first half. We only get training data from the first half because we're curious whether without training data in the second half, just with the PDE and the conditions, initial conditions, can we still reproduce what happens towards the later half? Okay. And now we want to get collocation points for the initial condition and the PDE. So here, I have 30 regularly sampled. So here, I actually don't need to do this manual seed because I'm not doing random sampling. So if you do random sampling, I would encourage you to manually set the seed. Right. So here, I will hide that. Okay. So I will comment that out. We actually don't really need this step. Doesn't make a difference. But if you do random sampling instead of uniform sampling, yeah, I would encourage you to have some reproducibility if you want. Okay, so here we are sampling 30 locations or 30 time points from 0 to 1 second. Don't forget to require grads is true. And also we want 1 point at 0 for the initial condition. Also require grads equals true. We'll run this. And moving on to section 4. So we will define a neural network. This is not very different in structure from the typical classic neural networks. So here, we have a few arguments. We want to specify how many variables I have as the input. Later, I will have one variable, which is t, as the input. So the first layer will start with one node, and then the last layer will end with the number of output, which is just 1 for the displacement x. So later my n output will also be 1 because I will have layers that end with one node. And here, with these two arguments, I specify how many layers I have in between. Usually, if we want a shallow network, this will not be a very large number. Actually, later on, we use three layers. And how many nodes we have in each of these hidden layers. So if we want a wide neural network, this will be a relatively large number. I think we can try something like 30 plus. That is very fair. So I also did some searching during the break on why we want a shallow and wide neural network. So why do we want it to be shallow? Having an overly deep neural network is not good for the derivative computation. The derivatives, right, yeah, exactly. It might be unstable, it might vanish. And also it will make the compute unnecessarily expensive because hopefully with the PDE, we don't need neural network to carry so much of the weight in reproducing all the variations. That's why deep neural network can be too expensive unnecessarily. And at the same time, why do we want it to be wide? So I see that a wide neural network can approximate continuous functions pretty well. And usually the kind of PDE that we want to reproduce are also this kind of continuous functions. So this kind of shallow and wide neural network is more similar to the flavor of PDE that we're trying to mimic. Yeah. And so here, this specifies that we'll pass our one input through bunch of hidden layers, and then it will give us the output. And okay, here comes the pin part. We can use it. I wrote a function for us to calculate the derivative. Just now in the slides, you notice that we did this autograd grad twice, once on the x to get dx over dt, and the second time on dx over dt to get second order derivative. So here I just combine this into one function. Basically, I want to just specify the output and input and get the derivative. And we can later apply this derivative function twice. So that's up to you whether you want to single this out as a function or you want to just use this line repeatedly in your code later. But here, because I need to use it 3 times, I just gave the function here. OK, so here, let's take a minute to pause here and think. So let's say we apply this derivative function to get dx and dx2, which are the first and second order derivative. We also have the predictions x at these collocation points. We now have these 3 ingredients. How can we use the 3 output above to calculate the physics residuals? And here, we will come back to this equation, right? We will plug them into this equation, and we'll also use the m and mu and k that we already defined early on. And then that will be our physics residual, right? So that's what you see right here. So we will run this. And this is, you notice, it's still a function. Because this will accept the neural network. It will also accept the collocation points. The collocation points here, in this case, they're always the same 30 points. That is true, but the models will change as we train the model, right? So ideally, we want to update the physics laws at every step. Every time we get a new set of model weights, we'll pass it through this ODE function that we define here. We get the prediction, we get the derivatives, get the residuals, and this will be our function to calculate ODE residuals. And similarly, we can write a function to calculate initial condition residuals. And that will be comparing the prediction at time t to the value of 1, because ideally, the initial condition specifies that x equals 1. And also, we want another initial condition that the velocity at time 0 is equals to 0. So those are the 2 residuals. Here we output both of them. And I just realized that are these too small for you to see? I can try to enlarge the font. Let me see if I can enlarge it. Is this better? Okay, how about this? All right. Okay, so now we have made the function to calculate the physics residuals. And here I want to add a little bit more visualization of how the physics residuals are working. So you can just run this code, but this will actually not be part of the workflow. This is just for us to demonstrate and explore whether our ODE function is working. So you don't have to care too much about the code that I have in there, but basically I put in a wrong model, a model that's quite off. Okay, so my exact solution is the blue one. I put in a wrong model that will give me this orange line, and I want to know, so let's say my neural network follows this wrong model, how much physics residuals would I see? So yeah, it gives me quite a large range of residuals, even to the magnitude of 150. And even if I later sum this up and multiply by a small number, it's still not a negligible number that I will penalize the model with. And we can see whether this residuals will vanish if we actually use the correct model. So here on the first line, I'm altering some parameters. So if you delete this +1 and you delete this omega 5, basically I'm trying to use the exact same, the true parameters of the system. All right. Now I'm expecting the altered model and exact solution, expecting them to be the same, and I'm expecting the residuals to be what value again? To be a very small negative, very small value close to 0, right? So yeah, you see now it's indeed very close to 0. So here, remember this is 1 times 10 to the power of -5, so it's like 0.00001. So these are really just tiny numbers, very close to 0. So this is, we know that if the model ideally gets to this true model, it will not be penalized, and we will get convergence. That is what a good model will do. So I encourage you to play with the altered parameters here. You can use this to kind of visualize that if you have a round model, how it's being penalized by the ODE function that we have here. All right. So this is not like a bit tangential. Now we come back to our actual workflow with a pin. Just now we have the few elements. We have the neural network, which is just a model. We have ODE, which will take the model and take the collocation points and give us the physics residual here. We'll take the residuals and calculate the loss from the physics loss. So here you can play with the model weight and see how that changes the model performance. And here's one anecdote about this harmonic oscillator example. The person who developed this, I think they tried a lot of different weights. It might look arbitrary that there's a 0.0001 here, but I've heard rumors that if you change this model weight, the pin will not work. So that's what I heard. And I would hope that you can play with the model weight and help me validate if that rumor is true, and think about why pin might fail sometimes, and really know that even pin is so fancy, it has a lot of limitations in a lot of cases. So yeah, for now, we'll stick to the known case that works, which is this particular model weight. And that gives us one of the loss terms. The second loss term is supposed to be about initial conditions. So we do have the residuals, and we're going to take the square. You can take the mean. You don't have to because it's just one number. And then you combine them, and you apply a weight. So you can apply different weights to different boundary conditions or initial conditions. If you think one of the conditions is more important than the other, yeah, feel free to assign different weights. So here we have the same weights for both of them. Don't forget we have the training data. So with the training data, we are going to compare those with the observed data and then use MSE to calculate the loss. And this pin wrapper here will output all the loss terms that we need. And later we will sum them up in the training loop when we do want to optimize the model parameters, the model weights. Okay, so have we run this? Yeah. Okay, now we want to write a training loop, basically to use the functions we wrote just now to optimize model weights using the loss terms. And here, you can do training and prediction separately, but I also like to do prediction and visualization as I train as well, so that I can monitor how my training is going. So that's what we are doing here. We are plotting as we train through every 5,000 epoch. So looking at the training loop, so we will first do a model wrapper. So basically applying the pin wrapper to the neural network that we specify. All right, what are the other important parts here? For example, we have an argument that specify how many epochs that we want to train for, and then we will loop through those epochs. And we will get the different loss terms using the pin wrapper that we mentioned. And they will give us these three things: the loss of physics, loss of initial condition, and data loss. And we'll sum them up to get the final loss. You also have the option to apply the weight here, so it's really just up to you whether you want to do the weighting within the wrapper or you want to do the weighting within the training loop. It's going to be similar in effect. Okay, and then these are the standard ones in the training loop. We're doing backward propagation, and let's run this. So now we have defined our training loop. We also need a function to plot the results. So you don't have to look into the plotting function here because it's quite case specific. And if you do want to generate your own plot, you can use the Gemini to, let's say, I want to generalize a visualization of predictions x over t, something like that. So one thing that is kind of different or peculiar here is that you notice I have a lot of these detached. So I have some of these detached because sometimes if a pin is very heavy duty, you have a lot of data, you want to do it in GPU rather than CPU. So usually there is a process to kind of transfer them from devices to devices. So this makes sure that I can grab the most updated variables and use them for plotting. All right. Okay. So this is the step that will take slightly longer time. So we will definitely run this and wait for it. So what is this doing? I personally like to set a random seed every time I try to get some reproducibility, but that's really up to you. And remember, we specified the neural networks that take a few arguments. We want a number of input variables to be 1, number of output variables to be 1 as well. 32 nodes in each layer, and we have 3 hidden layers, so that's a shallow and wide network. And we will put this neural network within the pin wrapper. And this wrapper, later, what does it do? If we use this wrapper, it will give us the 3 loss terms: physics loss, initial conditions loss, data loss, right? And we want to specify the optimizer that we use. Here we use an Atom optimizer. You can specify the learning rate, and I would encourage you to change the learning rate and see how that affects the outcome as well. So yeah, now with our specified training loop, we are ready to take everything together. We do have to feed it, for example, the pin wrapper, the optimizer, and the different input and output. Of course, for collocation points, you only have the inputs. You don't have the output. Output is just 0. It should supposed to be 0, right? Then for the data loss, you have both input and output, and specify the number of epochs. And here, again, you see the figure that I showed during in the slides. At training step 5,000 epochs, it's getting there. It's getting there. 10K epochs, okay, a lot better. And then here, finally, at 15K epochs, I think we have done a pretty good job. But like I said, play with model weights and see how that changes. Any questions up to this point? Yes, please.
Yeah, it looks that training data directly from the exact solution.
Right, yeah.
But in reality, maybe it has measurement, noise, how that affected performance.
Yeah, that's a great question. I think we discussed that a little bit during the break too. My hunch is that if we have noisy data, it's definitely the performance is going to suffer, but not as much as in a baseline neural network that doesn't have the physics. Because the physics, if we have in there, it's a pretty strong regularization to the neural networks. So it will, in a sense, to some extent, prevent the model from overfitting to the noise themselves. Yeah, if that helps. Yeah. But whether, how much it affects the performance, I think is very case dependent. So for this case, if we inject some noise to the training data, yeah, I think we can do exploration on this notebook. We can add a random number like that has standard deviation of 0.5 and something and see how that affects things. Yeah, and yes, you are right that in practice, we usually get these training data either from observations or we do experiments. Yeah. All right. And sometimes I think it's still fair game if you have the exact solution or numerical solution and you want to have some of those data used as training data. So in one extreme is that, for example, you don't have the physics at all, and you just have a lot of training data mainly from the simulation, numerical simulation, and you only use those data. You're then training a surrogate model in a sense. So you can still have those, and you can mix and match them. Observations together with the model simulated training data and together with physics. You can have all of them. Yeah. All right. And here, I leave this one chunk. It's exactly the same as above. This is for you to alter the arguments here. For example, you can alter the number of layers, the number of nodes, and you can alter the learning rate, the epoch number, and yeah, and see how it changes performance. I do want to show that in the end, I have an extra section of comparison with the standard neural network that doesn't have the physics. So here, I just write another training loop. Here, the loss, you see, it's only the prediction compared to the data, right? So it doesn't have the physics loss, doesn't have the initial condition. So how will this change the performance? If you run this, you will see the figure in my slides again, that even after we train to the 15K epochs, it's still doing pretty bad whenever we don't have training data. That's how it looks like. Yeah. So any questions for this notebook? If not, we will go back to the slide and talk about more about inverse problem. All right. Okay. So this case study, we are not going to cover the math of it. We are mainly focusing on the workflow of it, the logic of it. So this is a case study not in physics. It's actually in epidemiology, and we can think of this as like how COVID spread in the population, right? So this is the model. It actually has so many different states. So it's a lot more complicated in a sense, but it's still ODE because the independent variable is just time. It doesn't have prediction over space. We're just watching one population and see how these things change, including S, which is the number of susceptible people to this virus, and E is the number of people that are exposed, for example, being in close contact with someone infected. And you can imagine that E is going to be a function of S because the number of exposed is dependent on the number of susceptible. Yeah. And then third, we do have the number of infectious. So that will, again, be a function of number of exposed. And if, unfortunately, one person gets infected, there will be two outcomes. Either they're on their path to recovery, which is R, and the other scenario is that they actually, unfortunately, die from it. So that's the M here, mortality. And you notice that most of these are blue. Only one of the variable is green here. That is because only one mortality is sometimes what we observe. For example, if someone got infected and never reported, they just recovered, you probably don't have an accurate data. So our recovery is probably not very well measured. And the number of susceptible, oh, that's even harder to observe, right? I don't even know whether I'm susceptible to it. So there's very hard to get numbers on those. But we do have M. And we do know how these variables are related to each other conceptually, right? But what we don't know is that the parameters that really specify the relationship. For example, what percentage of S becomes E, right? So here are a set of equations to specify the relationship among these 5 variables. They are quite specific to the domain, so I'm not expecting that we learn the equations here, but I just want to show that these specify the dependency among these variables. For example, E is dependent on S, and for example, I is dependent on E and previous I. Yeah, and the other thing I want to note is that, yeah, there are these parameters, right, beta, alpha. So these determine how we get from the current state to these derivatives, which are the rate of change, like how does mortality increase, things like this. Right. For example, this mu t is once you're infected, what are the likelihood that you actually see mortality? Yeah, so this mu t is something we don't know, but we want to infer, we want to figure out through fitting a pin. Just now we mentioned that pin is double duty because we can do forward and inverse problem within one framework. So once we fit the pin, ideally we not only predict all these 5 variables, we can also get the values of these 4 parameters. That's the goal here. So notations-wise, I will call these 5 ODE states, I will call them S collectively. It's going to be a vector. And then there are the 4 ODE parameters. I'll call them omega collectively. And note that most of the ODE states are unknown except for mortality in this case. And none of the parameters are known either. So we can imagine there are a lot of moving pieces. So this model is actually trying to do a lot of things at one go. Okay, so we talk about the workflow here. We will start with the input, which is time, and we'll compute all these 5 different state variables, ST, via forward passing over the neural network. So here, this represents, again, a shallow and wide neural network. And now that we have ST, we're going to compute ds over dt. So this could mean the capital S over time or the E over time, blah, blah, blah. But basically, we have 5 different kinds of derivatives, right? And we can, of course, calculate higher order derivatives as well. So in the ODE that we want, so what do we need? For example, we need d capital S over dt. We need dE over dt. And that's what the automatic differentiation is going to give us. Here in this set, we don't really need higher order derivatives. So that's going to make our life slightly easier in the automatic differentiation. We just need to do it one time, right? And then we want to compute the loss FODE with a combination of these solutions and the derivatives and also the parameters in omega. So remember, for example, if we shuffle this equation around, the derivative of S over t plus beta t times this quantity, this is going to be 0. So when we calculate the residual, we need to use S, we need to use I, we need to use N, which is the number of people in this whole population. That one is fortunately known. And we involve this unknown parameter that is beta. We also involve this derivative. So that's how we try to calculate the residual for one of these but we have to calculate the residual for all of them, right? All 5 equations, and we can choose to add them up later. Right. So here, the residuals from step 3 and step 2, they will be minimized, and that is expressed in this term. So for example, here, this means that I compare ds over dt, that will be, for example, d over dt or d capital S over dt, together with the function of ODE. So this function actually predicts the right-hand side. So we compare the left-hand side to the right-hand side. So that's another way of doing things. We can either shuffle it, or we can just compare the 2 sides. Either way is fine. So you can make a function that calculates the right-hand side and compare it to this side, or you can make a function that takes the 2 sides together, and later you ask that output to be 0. Either way is fine. But the thing is, after we calculate that residual, we're going to make a square, and we're going to calculate a mean. And that's what we mean by summing them up and dividing by n plus 1. And note that we have a second component here. That is where we involve the ground truth data. Remember, we only have ground truth data, the observations for mortality. So we're going to see how the predicted mortality MT compares to, the predicted mortality MT hat compared to the observed MT. And that, again, for the data loss, we're going to calculate residual, square them, summarize them. So now with this whole thing as a loss function, we will try to minimize this loss. And as we minimize, we update both the neural network parameters or the neural network model weights, and also the physical parameters or the epidemiological parameters in this case, including, for example, the rate of mortality, mu t here. So I want to say that the methods, general methods here, they do not change. We just need to make the parameters omega t learnable. And you can think of that as adding, kind of like adding a node in the neural network that is not connected to anything else. It's only connected at a later point when we calculate the residuals from ODE, if that makes sense. So in the last tutorial today, we will talk about how to actually implement that and make the parameters learnable. So here, I want to mention a few special issues when we learn these parameters. Sometimes we want our parameters to be within 0 and 1, because, for example, mortality rate is a percentage. It's not going to go above this range. But this is not very friendly with our current setup. Our gradient descent doesn't have that constraint. So what we can do is that we add a layer to constrain that parameter. For example, our training, it can be using this, our neural network can be containing this raw parameter. It can exist in the real number domain. And then when we actually use this parameter to calculate, for example, the ODE loss, we don't want to use a real number. We want to use a transformed version of it. For example, using sigmoid here or using tan h here. Basically, different shapes, but the goal is the same, is to transform them to a variable that's within 0 and 1. So this guarantees that if, let's say, after training, you end up with a guess of this raw mortality rate to be 3, that's going to be okay, because this 3, after transformation, it will be just a value really close to 1. It will still be a reasonable, plausible parameter that you can use to calculate the ODE residual. So this will guarantee that. And I also want to put a note here that if you do use ReLU here, it is okay. I know that I mentioned in the neural network, try not to use non-smooth functions. But here, if you use a non-smooth function, it's okay because we are not calculating derivatives about this parameter. So we just need to make sure that everything that we do before we do the automatic differentiation, everything that leads to that is smooth. But if this is not related to the automatic differentiation, it's okay if it's not smooth. So you probably have had a sense that this is a really complicated problem with very scarce data. And we might need more constraints. Okay, we actually know more things in this domain. For example, we know some variables are monotonic with respect to time. And we can actually put this kind of domain knowledge into our loss functions. Here, I say low observability because there are a lot of moving pieces. We don't know the neural network model weights. We don't know 4 of the parameters. There are so many combinations of these parameters that can give similar output in terms of our MSE loss, right? So we probably need more constraints. And the examples here, for example, the number of susceptible people are going to be decreasing. For example, if you are already infected and you recover, you're immune. So basically, you're removed from this pool. This pool is going to get smaller, right? And then the number of recovery is going to increase over time. So these are the things that we do know. And we can constrain by adding this loss term into our loss function. And what this loss term is telling us is that ds over dt is going to be a negative number, right? It's going to have a negative slope at any given time point. And then on the other hand, dr over dt is going to have a positive slope. So that's why we use the ReLU to determine whether this gradient is positive or negative. Basically, if it's the direction that we're expecting, it's going to be 0. If it's not the direction that we are expecting, it's going to give a really large number, and we're going to penalize the model for that. And of course, we are going to still give collocation points, evaluate the derivatives as we did, and then we're going to summarize them. All right. So you can add this loss term to your existing loss function that already have the physics, already have the data loss, and that will have, hopefully, constrain your solution a little bit more. And the other domain knowledge that we have is sometimes smoothness. For example, the daily states might be changing a lot. For example, you might have a peak in infection or a peak in mortality. But the underlying parameters might not change that abruptly. For example, the mortality rate, it depends on how the virus is evolving. It does change over time, but it probably doesn't change very abruptly. So we can include a loss term to even incorporate this. Basically, we are asking that the parameters at different time steps, all right, they can be different, but hopefully they're not way too different. Right? We want to minimize the difference between them. And this will be our the shape of our usual MSE loss as well. And now we can add this loss term to our existing loss functions. So that's a few more tricks that you can do. So you can really mix and match all the loss terms that we have covered so far. If you don't have training data and you just want to rely on physics, sometimes that's okay if you have very good knowledge of the physics. And that is one thing that PIN users are proud of, that sometimes we say that it's like data-free. Or if you have a combination of them, or even if you have data combined with these constraints that are not strictly in ODE, that's also okay. Whatever domain knowledge that you can write into the loss function would be worth trying. Okay, now we want to talk about more conceptually some limitation solution and even some opportunities I'm excited about recently. And for this part onwards, we are not going to dive too deep into the math of it at all. So it's mainly just conceptual understanding, right? Do we have any questions at this point? We can take a pause here, a little pause. Okay. Okay, so now we're going to see the ugly parts of PIN. Nothing is too fancy here. So we face this problem, sometimes we call gradient imbalance. This has been empirically explored in this paper, and they consider a classical Poisson equation. This is not the case that they worked with in the paper per se, but I'm just using this to illustrate what a Poisson equation is trying to do. So in a surface, probably you have, for example, pollution at different sources, and you have outlets that are sinks. And you're trying to simulate that with the sources and the sinks, what is the concentration or how this variable is going to change over this continuous surface. That's the task that Poisson equation is going to do. So if we take this 3D figure and look at 2D, so these red points are where the sources are, where you have really high values, and these blue are where you have really low values. And sometimes, yeah, we know the physics, but it's quite a complicated one. If you, for example, increase the number of sources and sinks, or you let them alternate very fast. So this could be a challenging, interesting case for PIN. And here to explore, the authors of this paper, they obtained the data by simulating multiple values of C. You don't have to care about what C is. Basically, a larger C means that there's a faster alteration between source, sink, right? If it's a larger C, it's a harder physics problem. So their loss function, this is a key part. They have two kinds of loss, the PD loss and the boundary condition loss. And what they notice is that these two loss terms don't always contribute to model training equally. That's why they call it a gradient imbalance. So to illustrate this, gradient imbalance means that the gradients of PD residual loss, it's larger than the gradients of the others, right? So it kind of drives the optimization more so than the other terms. And here they have generated a histogram of gradients. The blue is the boundary condition loss gradient. So you do see them around 0. So there are some positive, some negative, but generally small. But then if you look at the orange, which are the gradient of PD loss, the gradients are a lot larger in the absolute magnitude. Basically, these orange, you see they're covering a lot larger range of gradients. So this tells us that the model is mainly learning from the PDE. It's not really learning from the boundary condition, even though we want it to be learning from both. Okay, so that is one realistic challenging, and it gets worse if our gradient imbalance is larger, because the error in the prediction will also be larger. So here they simulate, like I said, different complexity of this surface, and they notice that, yeah, the larger, if we start with a very simple problem, okay, the gradient imbalance is not that obvious. The orange and blue, they're still within the same zone. But if we are increasing the complexity and we look at the two histograms again, you notice that they're starting to be really different. And when we increase the C and making this gradient imbalance larger, our errors are also getting larger. So this is just to show that this is something that can affect our performance sometimes.
So can you just shed a little more light on layer 1, 2, 3, 4? What are they referencing?
I think those are the different hidden neural network layers.
So this is a calculation at each layer, or when I have 4 hidden layers versus 3 versus 2 versus 1?
My understanding is, my memory, if it's correct, is at every layer, but I might be wrong. I might have to check that paper again. Yeah. Therefore, yeah, sorry, I forgot about the details of that paper. All right. So fortunately, people recognize this issue and have developed a lot of solutions. Mainly is to play with the weights that we apply to each loss term. And we can even use adaptive loss weights. So the same author have developed, for example, two kinds of adaptive loss weights. The first one, they used it in a learning rate annealing algorithm. So basically, what this is showing is that we want to assign proper weight, lambda, to each loss term. This loss term could be boundary condition, could be initial condition, could be data and PD. But the goal is that we want the gradient multiplied by the weight to equal the maximum gradient descent, if that makes sense, to achieve the best that you observe in that epoch of training. So this update of the weight is calculated at the end of each epoch. And you can also do this not every iteration, but you can also do it at a fixed interval, like 5 iterations or something. That's also fine. But the trick here is to basically change lambda so that for each of your loss term, you try to make them similar after they multiply the weight. And the target is the maximum. And they also propose another way that we can just calculate the gradient of each weighted loss, and we take an average. Basically, after we apply a lambda, instead of max, we match the average of all the gradients. That's also fine. The goal is to make each term comparable, such that their gradients during backpropagation are very comparable in magnitude. And yeah.
What you mean to say is that we are maximizing the average of the volume of those three?
Pardon me? Sorry.
You mentioned like we are maximizing the average.
So here it's like you have a few different loss terms and you pick the maximum of those. So in the first method, they propose you can pick the max and then you update the weights so that after you multiply, they all match that max value. And the other version of this is that instead of taking the max, you take the average of all the possible gradients, and then you all match that mean. That's also fine. So second limitation is what we call spectral bias. So several studies pointed out that neural networks generally have difficulty. It's not specific to PIN, just generally for neural networks, they have difficulty learning very high frequency functions. For example, this on the left is a very high frequency function. You have like fast alteration between high values, low values, and you have these sharp edges here as well. These sharp edges are also high frequency. So these, if we learn it with a PIN, it's going to be pretty bad, if we use a vanilla workflow that we had so far. You see that the high values and the low values that it predicts is not really, it's like generally same in the location, but it misses the patterns, it misses the high frequency. And if we look at the absolute error, it's very patchy. It has a lot of patterns in the absolute error and very large values in the absolute error as well. So this is not ideal. And what do? We can use adaptive learning rates as a solution to it. So this is a little bit more theoretical that there's a neurotangent kernel theory, NTK. The key idea from this NTK theory is that if we have infinitely wide neural networks, they behave almost like linear functions, and we can use this NTK matrix to tell us if we update certain model weights, model parameters, how does each update affect the function output? Or if we change the input, how would that change the function output? So it's a very predictable, we try to predict the behavior of this neural network with NTK matrix. And specifically, NTK matrix has informative eigenvalues that tells us, for example, how quickly different regions are being learned. So that is useful. That means that we can use that to to adapt the learning rates. Basically, in the slow learning regions, we can give a higher weight, and the model will try to predict the high frequency, the difficult locations, the difficult areas better in the domain. And now after the adaptive learning rate is applied, you see that the exact and predicted are quite comparable. Yeah, the absolute error is still a little bit patchy, but a lot smaller in magnitude compared to the previous one. Yeah.
So how is this done? You are entering all the input values at the same time. So how are you able to alter the learning rate based on regions?
Yeah. My understanding, I need to go back to the paper and check, but I can think of different ways to do this. It could be, for example, you have different, you know that there are areas in this domain that are difficult. You give those, the PD loss from those points a higher weight. Does that make sense?
Can we choose the loss based on points?
Yeah, so if you have like two sets of collocation points, one is an easy area and one is a difficult area, so we can do that. Yeah, that's what I'm imagining, yeah. But it doesn't have to be done in a discrete way, I suppose, yeah. So each collocation point, we know that like whether it's in a difficult area or it's in an easy area or in an intermediate, and then in the model weight, yeah, we don't have to just use one number. We can assign weights for each set of collocation points. That's my understanding. And the other solution to this limitation is that we can change our input, right, using random Fourier features. This is to enrich our input. For example, our input, vanilla input, are coordinates in space and in time. But what if we take the sine and cosine of the coordinates? That will give us different information, right? And we can change the parameters in those sine cosine waves to make high frequency versions of those. And here you notice if I have one wave, I can probably simulate this square function that's very discontinuous, very high frequency. It's going to be hard, okay? It's not smooth, it's going to be hard for the neural network to learn. But if I add another wave of higher frequency, okay, if I overlay them, starting to get a bit more similar to this square wave. And then if I add a lot of different Fourier features with different frequency, okay, here I have a pretty good simulation. I have a pretty good representation of this square wave now. So this is what I mean by enriching frequencies. We will put them as additional input features. And in space, we have 2 dimensions. So just now I showed the 1-dimension case, but you can imagine that I can generate a lot of these random shapes over the space to fit to different high-frequency patterns in the domain if there are. And another solution is that we sometimes can scale features, and we can do feature expansion. So feature expansion overlaps a little bit with the Fourier features I talked about just now. So scaling is that we sometimes normalizing the input helps. And feature expansion means that there might be patterns that are relevant to the system. For example, if the pattern is periodic, you can have a sine wave. If the input t, you know that this process is going to have a fast decay over time, that you can put in the exponential decay as an input as well. And also you can put features on multiple scales. Yeah. All right, so the third limitation is what we call propagation failure. So this means that usually the solution at initial condition, boundary condition, are generally easier, but then the interior points are harder to learn. This is like when you try to heat up a metal plate. The edges will heat up faster than the center, but if you change it into another material like rubber, the center will heat up like even slower, something like that. So how would this propagation failure look like? So here, this paper talks about an example in a 1D convection problem, and the example is done with a beta that is convection coefficient equal to 30. So when beta equals to 30, this output, it varies with pretty high frequencies here over the domain defined by space and defined by time. All right. And then if we fit a pin, okay, it's going to be fitting pretty nicely to the boundary conditions, but then the interior points, it's not learning it at all. Yeah. And then they explore why is that so. It becomes harder if beta is larger, right? So when beta is so large, the relative error increases exponentially almost. So this also tells us, okay, on the other hand, when beta is smaller, right, it's probably easier for pin to learn. The propagation failure is less likely to happen. So what they proposed is to solve this with curriculum regularization. Basically, instead of finishing one optimization task at one go, we break it down into a sequence of subtasks. Basically, we start the neural network training with an easier PDE. In this case, smaller beta means easier. So the curriculum training in this orange line here will start with a very small beta. And after that, one training, it will get initialization, a good initialization of the neural network weights, and we'll take those weights, train it in a slightly higher value of beta, right? And then we ramp it up all the way to beta equals 30, which is the difficult case. All right. Now, after this, we see that the curriculum training pin is almost recovering the exact solution. Yeah, its performance is a lot better than what we saw just now, only doing the initial and boundary conditions. Right. So this makes sense. If we are facing a very difficult physics problem and we want to solve this complex PDE, maybe it makes sense to start our training from earlier, from an easier case of it, the case that's has even starting with purely boundary condition. It's just to ramp the model up to get good initialization of weights. Okay, this is the last limitation I'm going to talk about, which is inductive bias. So in a lot of typical networks that we are familiar with, like convolutional neural network, recurrent graph network, they take advantage of the thing called relational inductive bias. Basically, there are additional constraints. For example, in recurrent neural network, we know that there's a dependency over time. Your prediction over current time step might be dependent on the prediction over the previous time steps. And this is unfortunately not supported in the pin that we talked about so far, right? If you think about the traditional pin, we don't take advantage of this kind of relationship or structure because if we are trying to, for example, predict what's going on in this image, we will if we want to force it into a pin, we'll take the x and y coordinate, and we'll pass it through neural network, an even pin, and we'll get the red and green and blue levels that will predict what color this pixel is. But then it doesn't have any dependency with the neighboring pixels' values. But in this case, if we use our judgment, it does have dependency. Like this is in a block of hair that is supposed to be very similar in color. And over time as well, if we want to predict this time series, our only input is time, and we pass it through network. And if we don't take advantage of the dependency among time, that's also going to be not only giving us inaccurate predictions, but also falling short of using our own domain knowledge. So the traditional pins, they're called implicit neural representations. They only take the coordinate or time. They don't consider the dependency. So that's not a very ideal feature of pin. That's why there have been solutions to trying to solve this problem. For example, in these two papers, one of them combined pin with CNN, and the other connected pin to transformer, right? But you can imagine that there has to be some tweaking, some customization, because pin doesn't naturally support that kind of dependency. So what they do with this pin and CNN combination is that instead of having the CNN directly output solution to the PDE, the CNN will give us spline coefficients. And then these spline coefficients will later be fed into the PDE, right? So this is one kind of a hack to connect these two together. So by spline, these are local piecewise polynomial functions. So if we have spline coefficients instead of the RGB values at each grid point or at each pixel, we can use these spline coefficients to reconstruct the image. We can also take these spline coefficients to calculate some kind of PDE loss if we want. So that is one trick, one hack to be able to use both kind of networks. And the other is a combination of pin and transformer. So the trick here is that transformer doesn't really typically just accept a pair of coordinate and time. It usually needs a sequence, right? So what they do is they generate pseudo sequence. Basically, for every time point, they generate the embedding of a previous time point, 2 time steps ahead, all the way. It will be a short sequence. It will be passed through the transformer, but then only the last element is used to calculate the physics loss. So here, the transformer will work on this pseudo sequence, but the PDE loss part will only take the the last element, the focal element. So here we can balance the need of transformer to use the sequence versus pin to use a pair of raw output and one single output or a vector of output at the current time step. So there are a lot of these hacks around. We can make use of them. And this is a performance of how pin without the transformer is compared to pin with transformer. So here they're demonstrating that the loss landscape is going to be easier if we pair the pin with the transformer. The landscape will be smoother, and the local minima is going to be a single one, and it's also easier to optimize over this loss landscape compared to this one that is very sharp and it has a few local minima. That's very bad for a pin. Okay, and I'm gonna spend the rest of the time talking about a few trends I'm personally excited about. So you have probably heard of Bayesian neural network And people have apparently also tried this for pin. And the idea of Bayesian is that our typical neural network will give us model weights that are just numbers, right? One number for each one of these model weights. But in a Bayesian approach, we actually want to quantify the uncertainty in these model weights as well. And that will give us a lot of knowledge on how uncertain our pin output can be. So the idea of Bayesian pin is not drastically different from a Bayesian neural network without pin, but I just want to point this out that it does exist, that even in pin, people have implemented not deterministic model weights, but the model weights with uncertainty. That's why here you see each model weight has this distribution. But you can also imagine that this will be quite hard to converge because we are not satisfied with just having one set of these model parameters. We're shooting for a set of these distributions, right? It's going to be a little bit hard, but hopefully the physics part is going to provide sufficient information so that the convergence is generally not too hard. And we have talked about transfer learning for neural networks, perhaps, and people have also already done this for pins. And here is an example that they train a base pin with a representative configuration. But here the challenge is that their system might have very different initial conditions. And each initial condition might require a different, slightly differently tuned pin model. So they start with a pre-trained base model, and they fine-tune with different configurations. But each of these new configurations will have fewer training iterations. It will be easier to train. And another one that I find quite interesting is this extended physics-informed neural networks called X-pins. Sometimes our training data are too large, or we have too many collocation points. Whichever reason, our model might be too expensive to fit in one go. So people have tried splitting the domain into subdomains. And in each subdomain, they will train a different pin. But the challenge is that at the intersection, at the boundary of these domains, how do we make sure that the solutions are still smooth, are still continuous? Then here the trick is that they do enforce interface conditions to ensure continuity across subdomains. Recall earlier on, we mentioned that we want the parameter to be smooth, for example, over time. So that is one kind of condition to enforce that continuity. And here they have another interface condition to ensure that across different subdomains, the pins, even though they were trained separately, they're not going to give very discontinuous predictions. And the benefit is that we can parallelize the training across different subdomains, and this will be a lot faster in computation. So how well does this work? I find this graph very interesting. The exact solution behaves like this on the top. So we have some high values here, we have some low values here. And here for demonstration, they cut out the shape of a dolphin, just split this whole domain into two subdomains, inside the dolphin and outside the dolphin. Right? Then two separate pins were trained. The interface conditions were enforced. Then if we squint our eyes and look at the boundary, we can almost not tell whether this is from one model or two submodels. This is them trying to demonstrate that in this extended pin, we actually can parallelize training, but still achieve really good predictions, very smooth surface, even very comparable to the exact solution. Even though our domain selection is very, very arbitrary, it could be very weird in shape, but still, they managed to do it, right? Yeah.
So are those interface conditions shape functions? Can those be shape functions?
You mean the dolphin or?
Like the dolphin.
Oh, I don't know whether they use any particular function. I think they just chose a very funny and weird shape that to demonstrate that even with this weird segregation of subdomain, they still manage to achieve good continuity across subdomains. I don't know whether they use function at all. It's probably not. They probably drew it. Yeah, that's my understanding. Because if they had put the subdomain like right here at this straight line, you'd probably not be convinced because they don't look continuous anyways. But they put this dolphin here, so you can compare within and outside the dolphin. You see it's continuous, and then, yeah, we're really convinced. Okay, so we're ready to conclude what we have learned today. So pins, even though I talked about a lot of limitations towards the second half, I still want to say it's a very powerful idea, and it's also relatively straightforward to implement. Like you said, like you saw in the tutorial, it could be implemented in a few functions, and it does have drawbacks. For example, the difficulty in fitting very high frequency functions. So you will see these limitations, but then gladly there is an active community working on these solutions and working on also multiple tools. So I think this does overcome some of the limitations. Having a big community is always important to me. Lastly, I want to remind us that it's very powerful for solving PDE, especially when we don't need a lot of extrapolation, but it is not a replacement for the classical partial differential equation solving using either an analytical or numerical method. It's always good to compare them, and it's always good to especially like look at how the extrapolation works if we do need them. Okay, and if you're interested in using pin in your work, you can refer to this guide on how to train pins. They have a lot of tricks and hacks, yeah, if your model is not behaving the way you want. Okay, I think we can leave some time for questions and discussion. If not, we can get a head start on our tutorials, but let's see. Let's pause for a few minutes here. Okay, we do have 20 more minutes left before lunch, I think, right? Okay, I will want us to go early for lunch, so I will get started 10 minutes into the tutorial, and we go lunch, okay? So for the tutorial, I want us to open up the second one. At least we can talk about the problem setup, and then in the afternoon, we'll dive into how to set up the pin. All right, so again, for this notebook, you will copy it to your own drive, and then you can feel free to edit it. Feel free to use Gemini also. This will follow the same structure as I just mentioned. I try to make the function names as similar as possible as well, so that you can adapt functions if you need. So after we load the library, we're going to talk a little bit about this problem. Okay, so consider we want to maybe make a battery, right, with a chemical solution. And we want to know the relationship between this voltage and current when we have this kind of solution for our battery. So one trick, one technique that people use is called voltammetry. So basically, you have this electrode embedded. This electrode will give you the voltage that you desire, that you specify. And you have in this container this chemical solution. Maybe it's a new chemical solution that you don't really know about. Right? Now you're figuring out the property of this chemical. So we will manipulate the system by increasing the pressure, the voltage applied to this electrode. And you can imagine that when we apply this voltage or this electrical potential, this chemical will move around, the ions will move around in this solution. Sometimes it will get closer to this electrode, sometimes it will go further away from it. And how this reaction, how this voltage change the concentration of this chemical is very important, because the rate that this chemical moves toward or away from the electrode because of these concentration changes is going to give us the flux, or it's going to, in other words, it's going to generate current. And by increasing the voltage slowly, we will see this kind of trend. This is called a forward scan. We increase the voltage. We'll see the current increase, and then we will see it decrease. Then at that point, we reverse it. That's why we call it cyclic voltammetry. We reverse it. We lower the voltage now. And after we lower it, the current will get lower at one point, and then go back to the starting current. So this later half is the reverse scan. And after having these two scans, we know pretty well how this chemical solution is going to give us different current under different voltage. And we know a little bit more about this chemical solution when we try to use it, for example, in a battery. And
Are we changing
yeah.
polarities that the voltage is going from negative to positive?
Oh, yeah, great question. I'm not a physicist, but I can cheat by looking at this, I think. Yeah, the flux can be either positive or negative, usually.
I'm talking about the potential or the voltage.
Oh, voltage?
The x-axis.
Oh, x-axis. Yeah, it's also a range from negative to positive. Yeah, it's a range. Oh, sorry. Yeah, so we'll start from a negative voltage and we'll end somewhere positive voltage, and then we reverse it. And the two pathways are going to be different usually. Okay, so what is our task? Our task is to model how the concentration of this chemical, we call it C, how this concentration changes over time and distance from the electrode. So now we have two inputs, right? Time and distance from the electrode. This evolution, it does have a physical law. We don't have to know about the details, but we do want to briefly look at the structure of it. So we have dC over dt, which is how the concentration changes over time. And on the right-hand side, we have second-order derivative with respect to the position or distance from the electrode. And there's a diffusion coefficient. And this is usually a constant. So this is going to be a forward problem. We're going to assume that we know D. And then our task is just to predict the concentration change over space and time. And later on, how is this C prediction going to be helpful? It can help us predict, for example, the current change under different voltage at the forward and the reverse scan. So we know the PDE here. We also know something about initial and boundary conditions. For the initial condition, so a lot of these are our assumptions that we are going to just state up front. At the beginning of the experiment, okay, we assume that the chemical species is uniformly distributed throughout the whole solution, with a known concentration. We call it 1. Okay. So we assume that we know this. This is where we start to apply the voltage, and then we're going to see the chemicals really start moving, right? About boundary conditions, we can think about two kinds, either very close to the electrode or very far away from the electrode. Our input here is X, which is distant to the electrode surface. So it ranges from X to even the edge of the boundary of this container. We can specify that any way that we want, given our knowledge about the container, right? So we do know how this chemical concentration will behave at the electrode surface. This is not something that we assume, but we actually know this from physics as well. It is not fixed. It is dynamically related to the potential. So the concentration of this chemical species on the surface is governed by this Nernst boundary condition. Here, we're not going to go into the equation because I'm not a physicist and we don't necessarily require anybody to learn the physics here. But I do have a visualization. I do give the equations within the function. So don't worry, you're going to be able to compute this boundary condition automatically with the functions that we give you. Another condition, how about far away from the electrode? All right, so if we imagine that our container is infinitely large, we can assume that the concentration is undisturbed. It remains at the initial value, which is 1, right? Because the effects of the electrode do not reach that far. For example, if you have an electrode in a lake, you probably don't expect any change in any of the chemicals 1 kilometer away from the electrode, right? So that's something that we can safely assume as well. And in practice, we can't get infinite. We will just use a very large number, right? So here, in this box, we actually just specify some of the system properties that we do know. For example, the starting potential, the reverse potential, how fast do we do this scan? Like how fast do we vary these? Do we vary this voltage? Right. So these things we do specify. And here is the Nernst boundary condition that I promised. Don't have to learn the equation, but you just have to trust me that this function will reproduce what it looks like. Okay, so this figure here is saying that the surface concentration at x equals to 0 is going to be having this trend as I do the forward scan and then the reverse scan. It's going to start with 1. Okay, that's a bulk concentration. It's going to decrease all the way to 0. So basically the chemical moved away from the electrode until there's no more of this chemical at the surface, right? And then we do the reverse scan. It's going to slowly come back towards the electrode and go back to the initial value of 1. So this is the Nernst boundary condition at the surface of the electrode. And our target is to use the pin to learn how concentration changes over space and over time. What do we constrain it by? There is the Fick's law, which is the simple equation that has this one. 2 of the derivatives on 2 sides. We'll constrain it with this. And we'll also constrain it with the initial condition. And we'll also have 2 boundary conditions, one at the surface, one at the distant location. And yeah, so after we get the concentration, we can calculate other stuff. For example, how the current is going to change according to the voltage. And again, this is the forward problem. And yeah, we'll work on that in the afternoon. So I think we can pause here. Let me know if you have questions. If not, we can wrap up the morning session.